Welcome back to the 8th video about the Melexis MLX90363 Triaxis magnetometer. In the previous video, we were able to successfully write a 16-bit word to the EEPROM of that thing that holds the configuration. And that involved quite a lot. A total of 4 SPI transactions sending over 3 new messages from the master to the slave and decoding 3 new messages that come back from the slave to the master. Also looking up a key for writing to the EEPROM in a lookup table. Card here, link in the description. Now, being able to write raw 16-bit words to the thing's EEPROM is nice. But what we really want is to write specific configuration parameters to its EEPROM. And that's exactly what we will do in this video. Enjoy! So, how can we accomplish that while at the same time avoiding unnecessary writes to the EEPROM in our little chip? Remember, this thing has a limited lifetime when it comes to write cycles. Let's recap what we have so far. As mentioned in the previous video, we implemented a EEPROM write method that uses 6 different EESPI messages to write a single 16-bit word within the EEPROM. In the video before that, we've implemented a config read method that uses the 2 memory read messages to read out the relevant 16-bit words from the EEPROM and store them in a 16-bit integer words array inside a union config. And we called that union config actconfig. I changed that meanwhile, it's now active config. We've also implemented almost 24 methods, config xxxx, xxx being the name of the parameter within the EEPROM, that return us the value of that parameter within the EEPROM by accessing the struct values within the union config. The struct values, remember, is just a more sensible memory map of the unstructured data in the words array. Meanwhile, I renamed those methods too. They are now called active parameter name because they return us the active configuration parameter from the EEPROM stored in the active config union config. For example, unsigned integer 32 active user ID. Anyway, card to that video before the last here, link in the description. So, to write single parameters to the EEPROM, we basically just have to mirror the whole thing. So, for every active parameter name method that returns us the value of that parameter, we have to create, and I called them update parameter name, with the value of the parameter we desire as an argument. For example, update user ID unsigned integer 32 to value. These methods don't write directly into the active config, but instead into a mirrored target config of the type union config. And of course, they also write into the struct values. That will enable us to create a method commit config that compares the words arrays in the active config and the target config and only writes the changed words into the EEPROM using the EEPROM write method we implemented in the previous video. And yes, I borrowed the terminology of update and commit from SQL. We can update our parameters here in the target config as long as we want. We have to commit that config to the EEPROM so it will become the active configuration. In a first step, let's create for each type active xxx method that we have a void update xxx type 2 method. And I won't show you all the code, just, the interesting parts. I will try to avoid repetitions. And here are all the new methods in the public part of my library definition. So here is, for example, the existing method active map_xyz, formerly known as config map_xyz, which returns me the config parameter map_xyz as a enum_xyz. And then we have a new method, update map_xyz2, which gets as an argument such a enum. And of course, that's a void function, returning nothing. And I did that really for each and every function. So here at the end of our list, we have active free, which returns us a free struct with all the freely programmable bytes in the EEPROM. And now I have an additional update free 2 that gets as an argument such a free struct. And of course, again, returns nothing, like all these functions for setting a parameter. There's one exception, and this is in the old naming convention style, config MLXID, which returns us an unsigned integer 64 containing the 48-bit MLXID, which we shouldn't configure or change. I have to think about what we will do with that thing. Of course, we have now in the private part of our class definition, besides a config active config, formerly known as just act config, also a config target config. And here are the implementations of those new methods in the CPP file. As mentioned, I won't go over each and every one of them. I will just pick some examples, and those will cover all techniques used in these new methods. The first one we have a look at is update pin filter, which gets an argument, an enum pin filter. Please note that the enum pin filter does not really occupy all bits within the pin filter variable in our value struct. So in that first line, we reset all the pin filter bits in our target config by binary ending pin filter with the inverted bit mask pin filter. And then we set the bits again inside pin filter by binary ORing that with our argument. Update free gets as an argument a free struct. Remember that free struct just contains an array of 5 bytes, and we put that array into a struct so we can return it here in our active free function. Anyway, we just take those 5 bytes and we assign them to the free members within our value struct within our target config. Update k-alpha raw gets as an argument a 16-bit unsigned integer. And incidentally, our member here within the value struct k-alpha is also a 16-bit integer. So we just assign here the argument to that member within the target config and we're done. Update k-alpha is a little bit more complicated because it gets as an argument a float in the range between 0 and 2. All floats within those Melexis chips are obviously in the range between 0 and 2. Don't ask me why. Anyway, we first check if our argument is really in the valid value range. If that's not the case, we do nothing. Otherwise, we translate that value back to a 16-bit integer by dividing it by 2 and then multiplying it by 2 to the power of 16 minus 1 and rounding that result to an integer value, and then we use our already existing update k-alpha raw to set that in our target config. Update f hysteresis is a little bit different. It also gets a float as an argument, but in the datasheet we get the information that one least significant bit in the corresponding integer value is 0.044 degrees. And this time we only have an 8-bit integer. So we first check if the value is in the correct range, and 255 times 0.044 is 1.22. If that's not the case, we return. Otherwise, we translate that back into an integer by dividing it by 0.044 and round the result to an integer, and then use an update fhyst raw to set the value in our target configuration. Then we have methods that get a bool as an argument. For example, here update 3D. They basically work exactly the same like the methods that get an enum as an argument. At least here in the first statement, we just reset the bits in our target config. However, when it comes to the binary OR here, we have to check if the value is indeed true, and then we provide the bit mask. Otherwise, we provide just 0. An outlier when it comes to update methods that receive an unsigned integer as an argument is update selectivity mismatch raw. Because we provide here a 16-bit integer, the value is only 15 bits. So first we have to check here if our argument is in the correct range. So it's not greater than 2 to the power of 15 minus 1. And after that we handle the argument as if it was an enum. So first resetting the 15 bits within our target config and then binary ORing that to the argument. Update select sensitivity mismatch gets formally an enum as an argument, but that enum is really just a boolean with the values 0 and 1. We introduced that enum because the true-false semantics of a boolean didn't make sense here. So we handled the whole thing as if it was a boolean and just cast it here to an unsigned integer so we can check its logical value. And that's it. These were all the techniques used in the update methods. So we've implemented the update methods, and now we need to implement the commit config. We already talked about in the overview how the commit config method is comparing the words in the active and the target configuration and only writes changed words using the EEPROM write method, which we implemented in the previous video, to the EEPROM. Please note that the datasheet states that reboot must be sent after a series of EEPROM writes to make sure that the new EEPROM parameters are taken into account. So, our commit config also needs to execute a reboot to ensure that the chip is actually using the new values in the EEPROM. And at the very end, I would like the commit config also to call the config read so that the new EEPROM values are also within our active config. In addition, config read in the future should also write the read values from the EEPROM into our target config. That will ensure that after a commit config, all three contain the same values. In addition, I won't begin to call config read, so we don't forget about that. Here's the implementation of our new commit config method in the CPP file. The prototype is just in the public section of our class definition. I have here a local variable bool reboot required, which is initialized to false. Because if we don't change anything in the EEPROM, we don't need to reboot. Then I loop here through all my writable addresses. We defined that constant a while ago, I think also in the last video. And then I compare if the word I'm just processing is different between the active config and the target config. If that's the case, then a reboot is required, and I write that word from the target config to the EEPROM. If that fails, of course, I return false. If no reboot is required, that is, we didn't have to write anything to the EEPROM, I return true and we're done. Otherwise, I wait 135 microseconds, that's just T short, until we can send an actual reboot. And then we'll wait the 24, or to be exact, 20 at 5 volts and 23.5 milliseconds at 3.3 volts until the reboot is done. We reread the config into the memory and we return true. Here's a little change I made to config read. At the very end, I assign the struct values in my active config, which we just read, to the struct values in the target config. So they are both in sync again. Please note, you could always assign a struct to a struct in C++. However, with C++ 11 or above, I think you should also be able to directly assign a union to a union. But yeah, I'm staying here with the classic method. And here's a change I made to begin. At the very end, I do a config read, and if that fails, I return false. That's it. Now for the sketch to test everything. I made quite some changes to setup. The first being I added here an unsigned long milliseconds. We will use that below. Then I extended the whole setup of the serial port. That is what we had before, just a serial begin and then waiting for the serial to become ready. And I added that portion here, which basically waits for us to press enter in the serial monitor. So first I empty the serial buffer here, then I print out, press enter to start, then I wait until something comes available on serial, and then I throw that away too. The idea is here that when we upload the sketch, that we can actually see if the EEPROM is written to or not. Because remember, when you upload the sketch executes immediately, and if we don't wait, it writes the EEPROM. And by the time we open the serial monitor, the EEPROM has already been written to. Yeah. The read config after the begin is gone now, because the begin is reading the config now. And I'm no longer using here EEPROM write to write a single word to the EEPROM, but instead I use one of our update functions. I'm still working with the user ID, so I update the user ID here to an arbitrary value. Then I take a snapshot of the current millis in our new local variable, and I execute a commit config. If that fails, I handle the error as usual. Finally, I print out how long the commit config took. Remember, if the commit config is really writing to the EEPROM and rebooting the device, that takes quite some time, in the order of dozens of milliseconds. I also modified the loop. First, I have here now a static bool executed, which I initialize to false. Remember, static local variables keep their value even if the function is exited and re-entered. Then I check if executed is true. If that's the case, I exit my loop. And then we had that before, I do a serial print of the configuration. And afterwards, now I set executed to true. In effect, the loop will only, in its first iteration, print out the configuration. So I don't have to fiddle around with stopping the scrolling in the serial monitor. That's what that's really about. And here's, as always, how it looks at the serial monitor. So it waits now until I press enter. And then we have here the whole configuration. And commit config executed in 1 millisecond. Okay, and the user ID has exactly the value I set in the setup. However, let's close the serial monitor and change that to, let's say, BBBBCCCC. And upload the whole shebang. And open the serial monitor again. Okay, press enter to start. Let's do that. And now commit config took 107 milliseconds. So we were writing two words to the EEPROM and rebooting. And of course, our user ID is now BBBCCC. Now, let's see. Let's close that again and only change the last 16, the least significant 16-bit word in that 32-bit value and upload again. Okay, open the serial monitor, press enter. This time we only needed 69 milliseconds because we had only one EEPROM write operation plus the reboot. And if I do it again, we saw that in the beginning, we are basically taking no times, 0 or 1 millisecond. Great. I think we still have a little time left for some housekeeping. With the active and update methods as well as the commit config methods in place and begin calling config read, I can't see any use case where the application would directly call config read, EEPROM write, or the whole MOSI MISO message stuff associated with that. So we can move that all into the private section of our class. And that will also enable us to finally get rid of that rather redundant enum address. We are already in the private part of the class definition. Remember, that enum class address of type unsigned integer 8 was just an enumeration 1, 2, 3, 4, 5, 6, etc. of the words in our words array inside our typedef union config. And once upon a time, when we exposed those methods in the public part of our library, that made sense. So we had here with the enum class address a type which is self-explaining and safe because the value range is limited. But inside our library functions, we only access or used address inside of loops. More specifically, a config read looped over all the addresses, and then we had to cast it actually to the enum type address when we used the send memory read method. And commit config did the same, just a loop over all addresses, this time the writable addresses, and casting here our loop variable to the enum type address, which is BS. Anyway, all our formerly public functions related to the EEPROM, with the exception, of course, of update config, are now here in the private part of our library. And everywhere where I had an address with, formerly the enum type address, I'm now just using an unsigned integer 8. All that did in the implementation code was really remove a lot of cast operators. For example, before I had to cast here that unsigned integer address to the enum address before I could pass it to the EEPROM write. So a lot less cast operators. And I also found a solution for that config MLX ID, which I didn't touch in the beginning. I call that now simply info MLX ID. And I created two more info methods here, info firmware version and info hardware version. You'll see in a moment why. For these methods to work, I also created two new private member variables, unsigned integer 8, both hardware version and firmware version. And the magic all happens in our begin method. I tried to make it a little bit more bulletproof. Remember, sometimes we saw it throwing an invalid opcode error, and I was not happy with that. I added that code here between the reboot and our config read. And that basically sends another knob message to our slave, and then we should receive, after a proper reboot, a ready message. We saw these ready messages before live, card here, link in the description. The important thing is these ready messages contain the hardware version and the firmware version. And that's exactly what I extract here from that received message. The rationale here also being that normally in your application you won't reboot the chip by yourself. That's all done by the library whenever it's needed. So yeah, just have the hardware version and the firmware version ready after begin. Consequently, I added a serial print MLX90363 info function to our sketch, which just prints out all the information. Okay. And I call that function inside the setup right after the begin. And if you look at the serial monitor, our code is still exactly the same, with the exception of now printing out in the beginning the firmware version, hardware version, and the MLX ID, which is no longer printed within the, config stuff. That's it for today. We're almost finished with writing our library. However, we still have 6 messages to implement. 2 of these messages are for diagnostics purposes, and the other 2 messages, you can do some frequency measurements of an internal oscillator of that thing. I don't know how useful that is, but we will implement it, of course. Till then, bye!